Every time you log in to Netflix or check your bank balance online, maybe swipe your student ID right here at Tarleton, or even just track a package you ordered, you're not just like interacting with an app, you are actually having this quiet, pretty sophisticated conversation with a database. Have you ever thought about that? Just take a second and picture it. This constant kind of invisible hum of data being looked up, updated, managed really carefully behind every single click, every interaction you make. It's happening all the time, everywhere. The thing is, our whole digital world doesn't run on magic, right? It runs on databases. And getting the skills to design them, manage them, keep them secure, well, that starts right here with understanding SQL. Welcome to the Deep Dive. Today, we're taking a really essential journey into the core ideas of BCIS 4301, database theory and practice. Our mission for this deep dive is basically to demystify SQL for you. We want to take you from the basic theory to its really powerful real-world uses. So we're going to dig into how we design databases, how we develop them, and then implement them, focusing really heavily on what's called the relational model. This covers, well, pretty much everything from entity relationship modeling that's visualizing the data and this critical idea of normalization to actually writing SQL code. We'll also touch on database administration, look at some cool emerging database tech, and really dive into how these concepts play out in crucial real-world applications across all sorts of industries. This deep dive is really tailor-made for you, whether you're a student right here in Tarleton State University's Dr. Sam Pack College of Business, maybe a future business leader, or honestly just anyone curious about the language that basically powers our digital lives. Okay, before we really jump into the deep end with data, if you're finding this valuable or, maybe you have a classmate who'd be interested, please go ahead and hit that follow button, share it with them, and definitely remember to check out the episode description. We've put together a bunch of extra resources just for you, links to docs, practice exercises, maybe even some deeper dives on specific things we talk about. All right, let's unpack this maybe with a real world kind of feel. SQL, it isn't just some technical skill for, hardcore programmers. It's actually like a superpower for pulling out really important business insights. Like, think about a big retail company. Let's call them Red Cat shoes. How do they figure out which shoes are flying off the shelves? Which ones are just sitting there? Or how do they know who their best customers are, the ones spending the most money? Or even predict, say, which months are going to be huge for sales for their new sneaker line? It's all thanks to SQL. It's the language that lets them ask these big questions and instantly turn these huge mountains of raw sales data into actual intelligence they can use. Without it, they'd just be guessing, right?
Exactly. And what's really fundamental, is that almost every application you use daily, from giants like Amazon to your bank's super secure system, relies heavily on SQL. It's not just a language for talking to relational databases. It really is the universal standard. And this isn't just about simple day-to-day stuff like processing one sale at the counter. It's also absolutely critical for big picture strategic decisions. We're talking identifying sales trends over years, optimizing inventory across thousands of locations, even spotting weird patterns that might indicate fraud. SQL really is that universal translator. It turns our kind of abstract business questions into precise instructions the database understands and can process incredibly fast.
Okay, so how do we even begin to ask those questions? Where's the starting point for pulling information out of this, potentially huge database?
It all starts with two really fundamental keywords, select and from.
Select and from, got it.
Precisely. The select statement is where you tell the database what data you want to see, which specific columns or pieces of information you're after. And then the from clause tells it where to get that data, which specific table holds the information you need. So, for instance, if you just wanted to grab absolutely everything from a really simple sales table, you might write something like, select from simplified sales. That little asterisk is basically shorthand for give me all the columns. But, and this is a really crucial best practice, especially as you get into real-world systems, try to avoid using select in production kind or when you're dealing with really big tables.
That seems convenient.
It is convenient for quick peeks, definitely. But the problem is it forces the database to fetch every single column for every single row, even if you only needed, say, the product name and price. This massively increases what we call the I/O load, basically, how much reading and writing the database has to do, and it eats up way more memory than needed.
Right.
On a system with millions of records, this can slow your queries down from milliseconds to potentially minutes. It really impacts performance.
Okay. Like asking the library to read out every word in every book just to find one author's name.
Exactly that. A much better way, much more efficient, is to explicitly list only the columns you actually need. So for Red Cat shoes, if they just wanted product names and prices, they'd write select product name, price from simplified sales. It's cleaner, faster, and easier for others to understand.
That makes total sense. But okay, we rarely want all the data, even all the columns. What if Red Cat Shoes only wants to see sales for sneakers? Not boots, not sandals, just sneakers. That's still filtering, right?
That's precisely where the where clause becomes your best friend. It acts as your filter. It lets you specify conditions, and only the rows that meet those conditions where the condition is true get returned. So where category sneakers gets you just the sneaker records. Think of it like making your haystack as small as possible before you start looking for the needle. This lets the database work much smarter, scanning only the data it absolutely needs to, which speeds things up a lot. And SQL gives you a whole toolkit of comparison operators for your where clause. You've got for exact matches like color black, then, or sometimes less means not equal to. You have ADU for less than, greater than, and so on. These work for numbers, dates, even alphabetically for text.
So you could do like where price 100.
Exactly. Get all products over $100.
Oh.
And for text, besides exact matches, we have the like operator, which is super powerful for finding patterns. If Red Cat wanted products starting with men's, they could use where product name like men %. That %% is a wildcard. It matches any sequence of characters or even no characters.
Oh, cool.
And for dates, simple comparisons work too, like where sale date equals 2025-0101 to find sales from the start of 2025 onwards. The key is just being precise in your conditions.
Okay, so we can get all sneakers, but what if Red Cat wants to narrow it down even more? Say they only want black sneakers. Now we're combining conditions. It sounds like it could get tricky.
Right, and this is where AND and OR come in. They're your main tools, your logical operators, for building these more complex filters. And D means all the conditions you list must be true for a row to be included. So for black sneakers, you'd write where category sneakers and color, black, both have to be true.
Okay, straightforward enough.
Or, on the other hand, means any one of the conditions can be true. So where category sneakers or manufacturer name, Puma, would give you all the sneakers regardless of brand, plus any product made by Puma, even if it's not a sneaker. It kind of expands your results. Now, here's a critical detail, something that definitely catches people out, even experienced folks. When you mix AND and OR in the same where clause, you really need to use parentheses.
Ooh, why is that? Like order of operations in math?
Exactly like that. AND has higher precedence, meaning SQL processes all the ANDs before it looks at the ORs unless you tell it otherwise with parentheses. So imagine you wrote where category sneakers or category boots and manufacturer name Nike. You might think you're asking for Nike sneakers or Nike boots, but because AND comes first, the database sees it as give me all sneakers from anyone or give me only Nike boots. The AND part, category boots and manufacturer name Nike, gets evaluated first.
Oh, okay, I see. That's definitely not what I intended in that case.
Right. If you wanted sneakers or boots, but only if they're made by Nike, you must use parentheses to group the OR. Where category sneakers or category boots and manufacturer name Nike. Always use parentheses when mixing AND and OR. It makes your logic crystal clear, prevents unexpected results, and makes your code way easier for anyone else or you 6 months later to understand. And just quickly, there's also the not operator, which just reverses a condition, like where not color all black. Again, use parentheses if you mix it with the AND or OR.
That parentheses tip is gold. Definitely like math class flashbacks. Okay, so sometimes we don't want every single row, even if it matches our filters. Like if Red Cat just wants a list of the unique manufacturers they carry sneakers from, not every single sneaker sale.
Perfect use case for distinct. It does exactly what it sounds like. It eliminates duplicate rows from your results, giving you only the unique values. So for that list of unique manufacturers who sold sneakers, you'd write select distinct manufacturer name from simplified sales where category, sneakers. Even if Nike sold 500 pairs of sneakers, Nike would only appear once in that list. One important thing. Distinct applies to the entire combination of columns you select. If you did select distinct manufacturer name color, you'd get unique pairs. So Nike black and Nike white would both show up as distinct combinations.
Got it. Unique combinations, okay. And once we have the data we want, especially if it's for a report or something we need to analyze, just getting a jumbled list isn't always helpful. How do we make it easy to read?
That's where order by Y comes into play. It sorts your results based on one or more columns you specify. It makes the output much easier to understand. By default, it sorts in ascending order A to Z for text, smallest to largest for numbers, earliest to latest for dates. You can explicitly say ASC for ascending, though it's usually the default anyway, or you can specify DSC for descending order Z to A, largest to smallest, latest to earliest.
Can you sort by more than one thing, like by category, then by price?
Absolutely, and that's really powerful. For Red Cat shoes, say they wanted to see their most expensive sneakers within each color group. They could use order by color ASC, price DESC. This would first group all the black sneakers together, sort those from highest price to lowest, then move to blue sneakers, sort those highest to lowest, and so on. Order by Y doesn't change what data you get back, only the sequence it's presented in. Really useful for quick insights.
Okay, sorting is great for organizing. But what if Red Cat wants to know more than just individual sales? Like, what's the total money they made from sneakers versus boots? Or how many different products does each brand supply them with? We're kind of summarizing now, right?
Exactly. Now we're stepping into the real power of SQL for analysis. This is where Group BY and what we call aggregate functions become absolutely essential. Group BBY lets you take your rows, divide them into groups based on the values in one or more columns, and then you can run calculations on each of those groups separately. Some common aggregate functions you'll use all the time are count and E, which counts the number of rows in each group. SUM adds up all the values in a numeric column for the group. ADG calculates the average. MIN finds the minimum value, and MAX finds the maximum.
Okay, so how would Red Cat find the total revenue per category?
Good example. They'd write something like, select category, C price quantity, as total revenue from simplified sales group by category. See, the group by category part first gathers all the sneaker sales together, all the boot sales together, and so on. Then EC price quantity calculates the total revenue for each of those category groups. The AS total revenue just gives that calculated sum a nice readable name in the output.
Wow, okay, that's incredibly useful for getting that high-level view. But what if they only care about the really big categories? Say they only want to see categories that brought in more than $1 million. We're filtering after the summing, right?
Excellent question. That's exactly what the halving clause is designed for. Think of halving as a where clause, but specifically for filtering groups after they've been created and aggregated by group by. You can't use where to filter on the result of sum or count, because where filters individual rows before the group by even happens.
Okay, order of operations again.
Precisely. So to get only those categories with over $1 million in revenue, you'd add halving to our previous query. Select category, sum price quantity, as total revenue from simplified sales group by category having price quantity 100,000. This gives Red Cat just their top performing categories based on that revenue threshold.
Understanding group by Y and halving is really fundamental for any kind of business intelligence or reporting you do with SQL.
Okay, so that simplified sales table we used for examples was, well, yeah, simplified. It worked well to show the basics, but you're saying real-world databases aren't usually like that. They're more complex.
Oh, definitely. That single table was useful for illustration, but in reality, storing everything, customer name, address, product details, manufacturer info, sale info, all in one giant table is a really bad idea.
Why is that? Seems like it would keep everything in one place. It sounds convenient, but the huge problem is redundancy. Imagine storing a customer's full name and address with every single purchase they ever make. If they buy 100 items, you've stored their address 100 times. Now, what happens if they move? You'd have to find and update that address in potentially hundreds, maybe thousands of places. Did you get them all? What if you miss one? Now you have conflicting information. It's a recipe for errors and inconsistencies, not to mention incredibly inefficient storage.
Okay, yeah, I can see how that would get messy fast. So what's the alternative?
The alternative, and this is a core concept in database design, is normalization. The idea is to strategically split your data into multiple, smaller related tables. Each table focuses on one specific thing or entity. So for Red Cat shoes, instead of one giant table, you'd likely have a customer table with customer info, a product table with product details, a manufacturer table, and a sale table recording the transaction.
Okay, separate tables. But how do they relate to each other? How do you know which customer bought which product?
That's where keys come in. Each table has a primary key, PK. This is usually a single column, like customer ID or product ID, that contains a unique value for every single row in that table. It's like a unique ID number. Then, to link tables, we use foreign keys, FK. A foreign key in one table is a column whose value matches the primary key value in another table. So the sale table wouldn't store the customer's name and address. Instead, it would just have a customer ID column, a foreign key, that contains the unique ID of the customer who made the purchase. That ID then points back to the full customer record in the customer table, where customer ID is the primary key.
Ah, I see. So you only store the full customer details once in the customer table.
Exactly. Same for products. The sale table has a product ID foreign key linking to the product table. The product table might have a manufacturer ID foreign key linking to the manufacturer table. It's like a library catalog. The book is cataloged once with all its details and a unique ID. When someone borrows it, the loan record just notes the borrower's ID and the book's ID, not the entire book description again. It avoids redundancy and keeps things consistent. This whole process of organizing data to minimize repetition is normalization.
Okay, so normalization sounds smart. Splitting data makes sense. But now, if the data I need is spread across, say, the sale table and the product table, how do I get it all back together? Like, how do we find those sneaker sales again, now that the category sneakers is in the product table, not the sale table?
That is precisely what joins are for. They are the mechanism for recombining data from these related normalized tables. The most common type, and often the default if you just write join, is the inner join. An inner join combines rows from two tables based on a related column between them, almost always matching a foreign key in one table to the primary key in the other. The key thing about inner join is that it only returns rows where there's a match in both tables. If you have a product in the product table that has never been sold, so there's no matching product in the sale table, that product won't show up in the results of an inner join between sale and product.
Okay, only matching rows. So how would that sneaker query look now with separate tables?
Right. You need to connect sale and product using their shared product ID. The query would look something like this. SQL, select, sale. Maybe be more specific later. Product.category, product.price, S, product list price, sale. This is our left table, join. Product on sale, product equal product. This is the join condition, where product category, sneakers, filter on the join table. See that on sale producted D part. That's the crucial join condition. It tells the database how these tables are related, match the product ID from the sale table with the product ID from the product table. The result is like a temporary merged table containing columns from both, but only for sales that involve sneakers. And again, that select sale is okay for exploring, but using select with joins can get really messy fast. You get all columns from both tables.
Right, potentially confusing and probably inefficient too.
Exactly. It's much better practice to list out exactly the columns you need from each table, like select sale, sale ID, sale date, product name, product.category, product.price. It makes the query clearer, avoids pulling unnecessary data, and prevents potential confusion if both tables happen to have a column with the same name, like maybe a date added column. Be specific. Hashtag 2.3 chaining joins and table aliases for complex queries.
Okay, joining two tables makes sense now. But what if Red Cat wants even more info? Like, they want to see the sneaker sold, but also the name of the manufacturer for each sneaker. And that manufacturer name lives in yet another table, the manufacturer table. Can we link three tables together?
Absolutely. This is where the real power comes in. You can chain joins together. You just follow the relationships defined by your T's. So we know sale links to product via product date. And let's say the product table has a manufacturer I foreign key that links to the manufacturer table where manufacturer D is the primary key. We just add another join to our query. It would look something like this. SQL select S sale ID. Notice the S prefix. S sale date. P product name and PM manufacturer name MM from sale as S, assigning alias S to sale, join product D, PNS product D, product reversed, join manufacturer as M on MP, manufacturer D S second join, where P category sneakers.
Whoa, okay. What are the SPNM and the AS?
Great question. Those are table aliases. They're like temporary nicknames you give to your tables within that specific query. Using the AS keyword, though sometimes AS is optional, just say less often works too. Using aliases like S for sale, P for product, M for manufacturer makes the query much shorter, cleaner, and easier to read, especially when you have long table names, or like here, you're joining several tables. Instead of writing product name and manufacturer name over and over, you just write P product name and M manufacturer name. It reduces clutter and makes the logic clearer. They are invaluable for complex queries. And think about a more complex, real-world request. Maybe someone asked for a list of all products made by manufacturers based in Texas, which were sold to customers living in California.
Okay, wow. That sounds like it involved sale, product, manufacturer, and customer tables.
Exactly. You'd need to chain 4 joins together. Sale to customer on customer ID, sale to product and product to B, product to manufacturer on manufacturer. Then your where clause would filter on customer, state equals and manufacturer, state equals TX. SQL handles this kind of multi-table weaving really elegantly with these chained join-on clauses. Now, while inner join is the most common one you'll use, it's important to know it's not the only type. SQL also offers what are called outer joins. The main ones you'll encounter are left join, or left outer join, right outer join, and full join, Full outer join.
Outer joins, how are they different from inner joins?
The key difference is how they handle rows that don't have a match in the other table. Remember, inner join only keeps rows that match in both tables. A left join, however, keeps all the rows from the left table, the one listed first before the join keyword, and then includes matching rows from the right table. If a row from the left table doesn't have a match in the right table, it still appears in the result, but the columns from the right table will just contain NL values for that row.
Oh, okay. So when would you use that?
Imagine Red Cat Shoes wants a list of all their products, but they also want to see the date of the last sale for each one if it ever sold. You could do a left join from product, the left table, to sale, the right table. Every product would be listed. Products that have sold would show sale dates. Products that have never sold would still be listed, but the sale date column would just be NLL.
Okay, that makes sense. Keep everything from the first table, and right join is just the opposite.
Exactly. Keeps all rows from the right table, fills in NLs for non-matching left table columns, and full join keeps all rows from both tables, filling in NLs on either side where there isn't a match. It's like combining a left join and a right join. We'll definitely dive deeper into these outer joins later, but just knowing they exist and handle non-matching rows differently from inner join is important context for now. Think of it like Venn diagrams. Inner join is just the overlapping intersection part. Left join is the whole left circle plus the intersection. Right join is the whole right circle plus the intersection. Full join is everything in both circles.
Good visual. Okay.
One really critical warning about joins in general. Always double-check your on-end condition, the part that specifies how the tables relate. On-end table A.id equals table B.id. If you make a mistake here, maybe forget the on-end clause entirely or use the wrong columns, you can accidentally create what's called a Cartesian product or a cross-join.
Cartesian product sounds bad.
It usually is. It means every single row from the first table gets combined with every single row from the second table. If you have 1,000 rows in table A and 1,000 in table B, you suddenly get 1,000, but 1,000 was 1 million rows in your result. If you have millions of rows, well, you can imagine. It can instantly overwhelm your database, consume all memory and CPU, and basically crash your system. It's almost never what you actually want. So be meticulous with those on-end clauses. And briefly, you might sometimes see natural join. It tries to guess the join columns based on matching names. It's generally less recommended because it's less explicit and can lead to surprises if column names change. Stick with the explicit join.onend syntax.
Okay, we've spent a lot of time on getting data out of the database, selecting, filtering, joining. But databases aren't just static archives, right? They're constantly changing. New customers sign up, Red Cat adds new shoe styles, sales happen every minute. How do we actually put new information into the database?
Right. That's where the data manipulation language, or DML, commands come in, specifically insert. Insert statements are how you add new rows, new records into a table. The basic structure is pretty straightforward. Insert into table name, column 1, column 2, values, value 1, value 2. It's strongly recommended, really best practice, to always explicitly list the columns you're inserting data into.
Why is that? If you're providing values for all columns anyway.
Well, for a few reasons. First, it makes your code much clearer. You know exactly which value corresponds to which column. Second, it makes your code more resilient to changes. If someone adds a new column to the table later, your insert statement won't break if you've explicitly listed the columns you are providing values for. If you just relied on the default order and didn't list columns, adding a new column would break your code. So always list the columns. For example, adding a new customer to Red Cat's database might look like this. SQL.insert into customer id, first name, last name, state, email. Values 501 Jane Doe, txjane.doe@example.com. This creates a new row in the customer table with these specific values. Now, what about columns we didn't list? Maybe there's a phone number column or a date join column.
Good question. What happens to those?
If those columns have a defined default value in the table structure, they'll get that default. If not, they'll typically be assigned the value NULL. An NULL is an important concept. It doesn't mean zero or an empty string. It means the value is unknown or not applicable or simply missing. Understanding how NEL works is pretty important for data integrity. If we didn't know Jane's email, we might insert NUL for the email column. You can also insert multiple rows at once, often by selecting data from another table. Maybe Red Cat wants to archive old sales. They could do insert into sale archive, select from sale, where sale date 2014-01-01-1. This takes all rows matching the where clause in sale and inserts them into sale archive. But this brings up a crucial point about data integrity. When you insert a row, especially one with foreign keys, the database checks things. For example, if you try to insert a sale with a customer ID that doesn't actually exist in the customer table, the database will and should reject the insert. Same if you try to insert a customer ID that's already being used as a primary key. These rules maintain consistency.
Okay, inserting new data makes sense. But data changes over time. What if customer moves and changes their address? Or maybe Red Cat decides to run a sale and needs to update the prices for a whole category of shoes. How do we change data that's already in the database?
For modifying existing records, we use the update statement. The general syntax is update table name set column 1 equals new value 1, column 2 equals new value 2, where condition. You specify the table which columns to change, set column new value, and critically, you use the where clause to specify which rows should get updated.
Okay, that where clause sounds really important again. Because my understanding is, and this sounds terrifying, if you forget the where clause on an update, it changes every single row in the table. Is that right? Like, no, like, I sure.
You are absolutely 100% correct. And yes, it is terrifying. It's probably one of the easiest ways to cause catastrophic data loss or corruption in a database. An update without a where clause will apply the changes to every single row. Imagine accidentally running update product set price 10 without a where clause. Suddenly, every single product Red Cat sells costs $10. Yikes.
Oh, man. Okay, so the mantra is always use where with update.
Always, always, always. And here's an even better practice. Before you run your update statement, run a select statement using the exact same where condition. So before you run update product set list price equal list price at 0.90, where categories boots, to give a 10% discount on boots, first run select product name, list price from product where category equals boots. This select query acts as a preview. It shows you exactly which rows will be affected by your updates. You can check the count, check the current values, make absolutely sure it's targeting the right records before you make the change permanent. It's a simple safety step that can save you from disaster. And it's interesting, different database systems sometimes handle updates involving multiple tables slightly differently. Like MySQL lets you do ePotate sale, join customer on net set sale, status, shipped, customer.last order date, app number down, where all in one go. But SQL Server, for example, might require you to update sale and customer in separate update statements, maybe using a from clause with the join in the update to identify the rows. So it's always good to know the specifics of the database system you're working with.
All right, we can add data with insert, change it with update. But sometimes data just needs to go away permanently. Like maybe Red Cat discontinues a specific shoe model entirely and they want it out of the active product list. How do we remove records?
For removing entire rows, we use the delete statement. The basic syntax is pretty simple. Delete from table name where condition.
Okay, and I'm guessing, just like update,
Yeah,
that where clause is absolutely critical here too. Forgetting it would
Okay.
delete everything.
exactly the same danger. A delete statement without a where clause will delete every single row in the table, leaving it completely empty but still existing as a table structure. Again, the cardinal rule applies. Run a select with the exact same where condition first to preview exactly what you're about to delete. Select from product where is discontinued true before you run delete from product where is discontinued true. Verify before you destroy. And once it's deleted this way, unless you have a backup or you're inside a transaction you can roll back, that data is typically gone for good. For example, delete from product where product key a keys 30 removes just that one specific product. Now, deleting raises an interesting point about those relationships we talked about, referential integrity and foreign keys. What happens if you try to delete a record that other records depend on?
Like trying to delete a manufacturer record when there are still products in the product table linked to that manufacturer.
Precisely. How the database handles this depends on how the foreign key constraint was set up when the database was designed. The options are usually 1. Restrict, the default. The database will simply prevent the delete. It will give you an error saying you can't delete the parent record because child records still exist. This is the safest option. 2. Cascade. If it's set to cascade, deleting the parent record, the manufacturer, will automatically delete all the child records, all products linked to that manufacturer. This is powerful but can be very dangerous if you're not careful. Deleting one thing could wipe out huge amounts of related data. 3. Set NUL, set default. This means when the parent is deleted, the foreign key column in the child records, for example, manufacturer ID in the product table, will be automatically set to NULL or to a predefined default value, effectively breaking the link but keeping the child record.
Wow. Okay, so you really need to know how those relationships are configured before you start deleting things.
Absolutely. You need to understand the schema and the consequences. Because of this complexity and the desire to keep historical data, sometimes companies use a soft delete strategy instead.
Soft delete.
Yeah, instead of actually running delete, you just update a status column on the record, maybe set an isActive flag from true to false, or set a deleted date timestamp, the data is still physically there in the table for reporting or auditing, but your application logic just filters it out from normal views. It's often a safer approach, especially for critical data. So we've talked about DML insert, update, delete, which manipulates the data inside tables. But there's another category, data definition language, DDL, which changes the structure of the database itself. And the most drastic DDL command related to removal is drop table.
Drop table. That sounds final.
It is. Drop table doesn't just delete the rows like delete does. It removes the entire table structure, the columns, the indexes, everything, and all the data within it completely and permanently from the database. It's gone. Poof.
Okay, definitely something to use with extreme caution then.
Extreme caution is an understatement. The best practices here are non-negotiable in any serious environment. 1. Backup first. Always, always have a reliable, recent backup before dropping anything significant. 2. Check dependencies. Understand which other tables, views, or stored procedures might rely on the table you're about to drop. Use database tools to check for foreign key relationships pointing to this table. 3. Test in non-production. Ideally, test the drop script in a development or staging environment first to ensure it doesn't cause unexpected problems elsewhere. 4. Use if exists. For safety in scripts, you can write drop table if exists your table name. This prevents the script from failing with an error if for some reason the table was already deleted or never existed. And just like with deleting records that have dependencies, the order matters when dropping tables. If table B has a foreign key that points to table A, you must drop table B, the referencing or child table, before you can drop table A, the referenced or parent table. Trying to drop table A first will usually result in an error because table B still depends on it. Understanding your schema's dependency graph is crucial for these kinds of structural changes.
Okay, we've covered a lot. We know how to get data, join it, change it, even delete it, or drop tables. But just knowing the commands isn't the whole story, right? You mentioned writing better queries. What does that actually mean? How do we prioritize when we're writing SQL?
That's a fantastic question because it gets to the heart of writing professional, maintainable code. There's a common saying in software development, premature optimization is the root of all evil, and it applies to SQL too. So I recommend a clear priority order. First, above all else, correctness. Does your query actually return the right data? Is it accurate? A query that runs in a millisecond but gives you the wrong answer is completely useless, maybe even harmful. Get it right first.
Okay, correctness first. Makes sense. What's next?
Second, readability. Can someone else on your team or you, looking back at it 6 months from now, easily understand what the query is doing? Can they debug it? Can they modify it safely? Clean, well-formatted, commented code is crucial for long-term maintenance. Only then, as the third priority, comes optimization. If, and only if, your correct and readable query is running too slowly, and it's a query that gets run frequently or deals with very large amounts of data, then you start investing time in making it faster. Trying to optimize too early often leads to overly complex code that might not even be targeting the real bottleneck. Correctness, readability, then optimization.
Readability seems really key, especially for teamwork. What are some quick wins for making SQL more readable?
Oh, absolutely. Readability is huge. Some simple things make a big difference. First, use comments. Explain the why behind complex logic, not just the what. Why did you choose this specific filter or join? Second, use table aliases consistently when joining multiple tables. Product name is much clearer than product. Product name when you've got 5 tables joined together. Third, prefer explicit join on insex over the older style of putting join conditions in the where clause. It clearly separates filtering logic from joining logic. Fourth, formatting matters. Be consistent. Put each selected column on a new line. Put each condition in your where clause on a new line, maybe indent it. Use capitalization consistently, like keywords select, from, where in uppercase. Even little things like where you put commas add up. It just makes the structure immediately visible. Hashtag tag 4.2, understanding query execution order and minimizing search space. So beyond making it readable, when you do need to optimize, it helps to have a mental model of how the database generally processes a query. Now, the internal query optimizer is incredibly smart and might reorder things, but the conceptual order often looks something like this. 1. From and joins happen first, identifying the initial large set of potential rows. 2. Where filters those individual rows. 3. Group by aggregates the filtered rows into groups. 4. Having filters those aggregated groups. 5. Select determines the final columns to output. 6. Union, if used, combines results. 7. Order by sorts the final output.
Okay, so there's a logical flow, even if the optimizer mixes it up sometimes. How does knowing that help with optimization?
The key principle is to eliminate unwanted data as early in that process as possible. The fewer rows the database has to carry through to the later, more expensive steps like grouping or sorting, the faster the query will be. So, for instance, always try to filter rows using where before you filter groups using having. The where clause runs earlier, reducing the number of rows that even need to be considered by group BY. Filtering early makes a huge difference. It's like trimming branches off a tree before you try to carry it makes the whole job lighter.
Right. Filter early. Makes sense. Now, when a query is just plain slow, even after we've tried to filter smartly, what's the big tool people reach for? I feel like I've heard the term indexes.
Indexes, yes, absolutely. They are usually the single most effective way to speed up slow select queries. Think of an index like the index at the back of a thick textbook. If you want to find every mention of normalization, you don't read the entire book cover to cover.
No, you just look up normalization in the index and it tells you exactly which pages to go to.
Exactly. Indexes work the same way for databases. Without an index on a column you're searching, like in a where clause or a join condition, the database might have to do a full table scan reading every single row to find the ones that match. It's slow, especially on large tables. An index is a separate data structure that the database maintains. It stores the values from the index column or columns in a sorted order, along with pointers back to the actual rows in the table. So when you search for a specific value, the database can use the index to very quickly locate the relevant rows, just like using the books index. It's like giving your database a GPS.
So you should just index every column then?
Not so fast.
Oh,
that leads to the problem of over-indexing. While indexes dramatically speed up read operations, they actually slow down write operations, insert, update, delete.
Okay.
Because every time you change data in an indexed column, the database doesn't just have to update the table itself, it also has to update every index that includes that column to keep it consistent. The more indexes you have, the more work the database has to do on every write. It's a trade-off. So the key is strategic indexing. You want to create indexes on columns that are frequently used in where clauses, join conditions on clauses, and sometimes order by clauses, but avoid indexing columns that are rarely searched or frequently updated if the read benefit doesn't outweigh the write cost. And there are different types of indexes too, like clustered versus non-clustered, primary versus secondary, even more advanced types like composite, multi-column, or partial indexes. But the core idea is providing those fast lookup paths, hashtag 4.4 smart where clauses, and avoiding common pitfalls. Now, even if you have the right indexes, how you write your where clause can still make or break performance. There's a concept called making a query sargable.
Sargable, that's a new one.
Yeah,
Sounds like pirate treasure.
Not quite, though finding a performance boost can feel like treasure. Sargable comes from search argument able. It basically means, is the condition written in a way that the database can actually use an index to satisfy it? A common way to make a query non-sargable and thus prevent index usage, forcing a slow table scan, is to apply a function directly to the column in the where clause. For example, writing where year order date equals 2023. Even if you have an index on order date, the database can't use it effectively because it has to first run the function on every single row's order date value before it can check if it equals 2023.
Okay, so the function on the column messes up the index lookup.
Exactly. The sargable way to write that same logic would be where order date equals 2023-0101 and order date 2024-0101. Now, the order date column is untouched on the left side of the comparison, and the database can use an index on order date to quickly find rows within that date range. Other things to watch out for. Using like with a leading wildcard, like where name like %Smith%, that initial % usually prevents index usage. Where name like Smith%, where the wildcard is only at the end, can often use an index. Also, generally prefer for exact matches over like if possible. And sometimes, using exists with a subquery can be faster than using in, especially if the subquery returns many rows, because exists just checks for the presence of any match and stops, while in might need to process the entire subquery result first. Being mindful of startability is key to writing efficient where clauses. Hashtag 4.5 optimizing joins and set operations. Optimizing joins also follow some key principles. First, as we mentioned with filtering, join only the tables you absolutely need data from. Don't add extra tables to the join if you're not selecting columns from them or using them in your where clause. Second, filter data before joining if possible. If you can apply where conditions to individual tables before they get joined, you reduce the number of rows that need to be processed by the join operation itself, which can be a huge win. Also, remember that inner join is often inherently faster than outer joins, left, right, full, because the database doesn't have to do the extra work of figuring out which rows don't match and generating those NLL values. If you don't strictly need the non-matching rows, stip with inner join.
And you mentioned joins can be faster than subqueries sometimes.
Yes, often joins perform better than correlated subqueries, where the inner query refers back to the outer query for each row. The database optimizer usually has more sophisticated ways to handle a single join operation than running a subquery repeatedly. This also helps avoid the n+1 query problem common in application code. That's when your code fetches a list of things, one query, and then loops through that list, running a separate query for each item to get related details, n queries. A single SQL query using joins can often fetch all that data at once, dramatically reducing database round trips and load.
Okay, that makes sense. One query is better than potentially hundreds.
Exactly. And one last quick tip on set operations, union and union all. Both combine results from multiple select statements. Union automatically removes duplicate rows from the final result. Union all does not remove duplicates. Because union has to do the extra work of identifying and removing duplicates, which can involve sorting, union all is significantly faster. So if you know your combined results won't have duplicates, or if duplicates are acceptable, always use union all for better performance. Use union only when you specifically need unique rows. #tag 4.6 Advanced Optimization Tools and Strategies. So we've talked about principles, but how do you actually know why your specific query is slow? How do you diagnose the bottleneck?
Yeah, how do you peek under the hood?
Most database systems provide a command, often called explain or explain analyze, or graphical tools like show execution plan in SQL Server. This is an incredibly powerful diagnostic tool. You run explain analyze followed by your actual query, and the database gives you back its query execution plan. This plan details exactly how the database intends to execute or actually executed your query. It shows you which tables it accessed, in what order, whether it used indexes or did table scans, the type of join algorithms used, the estimated or actual number of rows processed at each step, and the estimated or actual cost or time for each operation.
Wow. So it really breaks down the whole process.
Totally. It lets you pinpoint the bottlenecks. Are indexes being ignored? Is a particular join causing massive row expansion? Is it spending all its time sorting? Analyzing the execution plan is the key skill for serious SQL performance tuning. Another tool for managing complexity, especially in long queries, is common table expression, CTEs, which you define using the with keyword. Think of CTEs as named, temporary result sets that exist only for the duration of a single query. You can define a block of SQL, give it a name, and then refer to that name later in your main query, almost like referencing a temporary view.
So it helps break down complex queries.
Exactly. It makes long multi-step queries much more readable and modular. Instead of deeply nested subqueries, you can define each logical step as a CTE, building up your final result piece by piece. Great for readability and maintainability. We also talked about normalization being good for data integrity, but sometimes for very read-heavy applications like reporting dashboards where query speed is paramount, people might use strategic denormalization. This means intentionally adding some controlled redundancy back into the tables to avoid expensive joins. Maybe you store the customer state directly on the order table, even though it's technically redundant, it's already in customer, just to avoid joining to customer every time you query recent orders for a dashboard. It's a trade-off. You sacrifice some write efficiency and purity for faster reads. And finally, for truly enormous tables, we're talking billions of rows databases often support partitioning. This lets you physically split a huge table into smaller, more manageable chunks based on some criteria, like date ranges, maybe one partition per month. Queries that only need data from specific partitions, e.g. cells from last month, can run much faster because they only need to scan the relevant partition, not the entire multi-billion row table. It's a key technique for scaling very large databases.
Okay, we've got all these powerful commands, update, delete, drop table, that can permanently change or destroy data. This raises a really critical question. How do we test our SQL code safely? How can Red Cat Shoes test a script that updates prices without risking messing up their actual live sales data?
That is probably the most important operational question. And the absolute first rule, the one you never ever break, is never test on a production database. Period. Full stop.
Right. Seems obvious, but probably needs saying.
It always needs saying. You always need a dedicated non-production environment. This could be a development server on your own machine, a shared staging server that mimics production, or a specific test database. For really reliable testing, especially automated integration tests, the best practice is often to start each test run with a completely fresh, known state. This usually involves 1. Running scripts to create the necessary table structures, schema. 2. Populating those tables with a small, specific set of test data relevant to the test case. 3. running the actual code or SQL script you're testing, your insert, update, delete. 4, running verification queries, SQLs, to assert that the database is now in the expected state. 5, tearing down, cleaning up by truncating or dropping the table so the next test starts fresh. Another really useful technique, especially for manual testing or debugging data modification queries, is using transactions.
Transactions, how do those help with testing?
Most SQL databases allow you to explicitly start a transaction using a command like begin transaction or start transaction. Then you can run your update or delete statements. The changes you make are only visible within your current session and aren't permanent yet. You can then run select queries to check the results. If everything looks perfect, you can issue a commit command to make the changes permanent. But if something went wrong or if you were just experimenting, you can issue a rollback command. Rollback instantly undoes all the changes made since the begin transaction, leaving the database exactly as it was before you started.
Ah, so it's like a temporary sandbox with an undo button.
Exactly. It's an incredibly powerful safety net for testing potentially dangerous operations without permanent consequences until you're absolutely sure. And modern development workflows often use things like Docker containers to spin up isolated, pre-populated database instances just for testing, or even in memory databases like SQLite for super fast unit tests. The key is always having a controlled, safe environment separate from production. Hashtag 5.2 ethical data updates and audit trails. Now, this ability to change data raises a question that goes beyond just technical safety. It touches on ethics. When is it actually okay, ethically speaking, to go into a production database and directly modify or delete historical data?
That's a deep question. Like, fixing a typo seems okay, right? If someone has spelled a customer's name.
Right. Correcting a clear, factual error to maintain data accuracy seems generally acceptable, even necessary. But what about manipulating records to make sales numbers look better for a past quarter? Or deleting customer complaints that might look bad? That crosses a line, doesn't it? It's moving from accuracy to manipulation, potentially undermining trust in the data itself.
Yeah, that definitely feels wrong. So how do companies handle this? How do they balance needing accurate data with being transparent and ethical about how that data might get changed, especially using powerful tools like SQL?
It really is a tightrope walk, and responsible organizations put strong processes in place. First, any direct data modification in production should be a rare event, typically requiring approvals and strong justification. Second, and crucially, is the implementation of robust audit trails or change logs. These are systems, often built into the database or application layer, that automatically record every significant change made to the data.
What kind of information do these logs capture?
Typically, they capture the 4 Ws. Who made the change, which user account, or maybe which automated process. What change was made, often logging the table, column, primary key, the old value, and the new value. When the change occurred, a precise timestamp. And often, why the change was made, requiring the person making the change to link it to a support ticket, bug report, or provide a reason.
Yeah, so it provides full accountability in history.
Exactly. It ensures accountability. It provides a verifiable history if questions arise later. Why does the sales figure look different now? It allows auditors to track changes. If a correction needs to be made, like fixing that typo, the correction itself is logged, showing that a change occurred, who did it, when, and why. It's not about hiding changes, it's about making them transparent and traceable. This is absolutely essential for maintaining data integrity, building trust, and upholding ethical standards. The data needs to tell the true story, even when corrections are part of that story. Hashtag tag outro.
Wow, what an incredible deep dive today. We really have unpacked a lot about the fundamental power of SQL. We went from basic select queries and the analytical tools like group by and having, through connecting data with complex joins, and into those really critical commands for changing data. Insert, update, and delete. And remember those key takeaways, those golden rules. Always get it correct first, then make it readable, and only then worry about optimization if needed. For update and delete, never forget that where clause, and use select first as your safety check. Understand your data relationships, how normalization works, and use joins to bring that scattered information together to get the full picture. And we also touched on really crucial aspects like optimizing query performance with smart indexing and filtering, and importantly, the ethical responsibilities that come with having the power to manage and modify valuable data. So yeah, the next time you log into Netflix, check your bank app, swipe that Tarleton ID, or try that package, you'll know it's not some kind of digital magic happening. It's SQL. It's elegant, incredibly powerful language, working constantly, silently behind the scenes, making pretty much everything in our digital world actually function. Keep exploring this stuff. Keep asking questions. The world of data is just massive and fascinating. If you found this deep dive useful, please do share it, maybe with a classmate or just anyone who's curious about how technology really works. And don't forget to follow us for more deep dives. All those resources we mentioned, extra reading, practice sites, they're all linked right there in the episode description for you.
And maybe just a final thought to leave you with. If databases, these sort of invisible engines driving everything, just suddenly vanished tomorrow, what parts of your everyday life would grind to a halt first? Your morning coffee order, your online classes, your texts, your ability to buy groceries. It's kind of startling when you think about how dependent we are, isn't it? Behind every login, every tap, every swipe, every purchase, there's a database making it all possible. Until next time, keep exploring the world behind the data.